Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will implement support vector machine classification from scratch using Python. Right. So if you haven't seen my support vector classification video in which I had explained everything in detail for the support vector classification from geometric intuition and mathematics behind it. Right. So please check out that video in my playlist. So let's get started. So let's first understand what was our optimization function, right? So because we need to differentiate it with respect to W and B to apply gradient descent, right? So let's understand that first. Okay. So if I say in SVC, let me write it here. SVC, our optimization function was we need to find W which will minimize norm of W divided by 2 plus C times 1 by n is equal to 1 to n eta, right? And our constraint was yi into W transpose xi plus b would be greater or equal 1 minus eta, right? Where yi belongs to minus 1 or 1. Yeah. So if we see the binary classification, so our y could be minus 1 or 1, right? So this was our optimization problem, right? So I'm just modifying this equation slightly. So first, let's say yi into W transpose xi plus b greater or equal 1 minus eta. So here we have eta, right? So we can rewrite this equation. Let's say eta is equal to, or let's say a greater or equal to, let's say, right? So it can be 1 minus yi into W transpose xi plus b, right? So this would be our loss, which is basically called as a hinge loss, right? Okay, and if you see here we have norm of W divided by 2, right? For simplicity, we are replacing norm of W with norm of W square. So this is basically L2 norm, or you can say equivalent distance, and we are applying power of 2. So if you see, if you are minimizing, let's say x, so it is equivalent to you are minimizing x square as well, right? Because x square is increasing function, right? So in this case, we can write this power of 2. It will not change our optimization problem itself, right? So let me rewrite our optimization function would be W star find optimal W which will minimize, let's say, square of norm of W divided by 2 plus C times 1 by n is equal to 1 to n 1 minus yi into W transpose xi plus b, right? Okay, so now we need to find a derivative or differentiation with respect to W and B, right? It will help us to apply gradient descent. So let's first see, let's consider this as an we need to differentiate with respect to W. So now let's consider this first step only, first part of this equation, right? So it is norm of W square by 2, right? So what is norm of W? So we can rewrite it as a, let's say, W transpose W raised to 1 by 2, right? Right, and we are using a square of it here, right? This 1 by 2 will be same, so we can rewrite this as this. So 1 by 2 raised to 2 would be cancelled, and we will end up with 1 by 2 W transpose W, right? And if you see, W transpose W can be written as sigma I is equal to j, I is equal to 1 to j, let's say j is equal to 1 to n. Let me rewrite it. So basically it is size of w we are iterating. Let's say I is equal to 1 to n, and this is basically wi square, right? Because if you see in w transpose w, which is basically a dot product of w, we are just simplifying. If you write, let's say a dot b, right? So it will be a1 into b1 plus a2 into b2 and etc, right? So here we are doing same thing because we are having a or b here, but in our case we are using w transpose w, so it is multiplying w itself. So it would be w1 into w1, right? So it will become w1 square. So we are writing same. So if you derive this equation or differentiate this equation with respect to w, then we will have 1 by 2, let's say wi square by del w. Then what we will have? We will have 2 into wi divided by 2 total, right? This 2 would be cancelled and we will end up with only w, right? Because when we update the weight, we will update each weight. We will not taking sum of that, right? So it will be minus from wi will be minus from wi of the old value, right? So we derive this first part. So we can write del by del w. First term would be our w plus 1 by c sigma I is equal to 1 to n 1 minus yi into w transpose xi plus b, right? And we need to differentiate this part, right? So if you see, this w plus would be same. Sorry, this is not 1 by c but c, my mistake. It would be 1 by n there, right? So it is basically c times 1 by n, right? So okay, let me erase this. Okay, so let's say this c would be same. We are just differentiating this part. So if you differentiate this part, let's say del L by del W 1 minus yi into W transpose xi plus b with respect to W, right? So then it will become c times. So if you differentiate this 1, it is constant, so it will become 0, right? 0 minus yi would be there as it is, and now this term W transpose xi will become xi, that derivative of W with respect to W will be 1, right? And plus this b is treated as a constant, so it will be also 0, right? So we will end up with W plus c star minus yi into xi, right? So what would be our final equation will be, let's say consider this as an optimization function, del L by del W is equal to W plus c into minus yi into xi. This can be further simplified as a W minus c times yi into xi, right? Let's say dll by del W. Okay, so just remember this equation, I would say. And now we need to differentiate it with respect to b, right? So if you see, our original equation was, let me rewrite it again, W star is equal to norm of W divided by 2 plus c times 1 to n 1 minus yi into W transpose xi plus b, right? So now we have to differentiate this with respect to b. Then this term will be 0 because w will be treated as a constant, so this will be 0 c times this one will also be 0 because it is constant, so it can be 0 minus yi will be same multiply this term also will be treated as a constant because it don't have b in it, right? So let's say 0 plus b, then if you simplify it will be c times minus yi, this b will become 1, right? Let me write it here, because the differentiation of b with respect to b will be 1, right? So this is with respect to b, and c is our hyperparameter we had seen in the SVM classification video, right, when we are deriving this equation. So in summary, our optimization function, let's say del L by del W, with respect to W it will be W minus c times yi xi. So let's write W minus yi into xi, and with respect to b it will be simple minus yi, right? So c is our hyperparameter, we are multiplying it, so here it will also multiplied, right, in equation. Okay, so we will use this differentiation to update our weights, right? So let's go to Colab notebook and implement this. Okay, so let's implement. So first I would require one library to import, which will be numpy. Import numpy is np, right? Let's define a class, let's say soft margin svc, right? Let's define init method, self, let pass. First define the methods which we will gonna implement, right? So let's say first define initialization init method, right? And next it would be a fit, and then let's say predict, right? Okay, let me pass. Okay, so what are the parameters we would require? Let's say first we would require learning rate, right? Learning rate, let's default it will be 0.01. Then we would require c, let's say c is also 0.01 initially. Let's say how many times we need to perform operation gradient descent, like n iters. So this is basically how many times we need to pass our whole data set to process gradient descent, right? So let's say 1000 times, right? Now just assign this variable learning rate self dot c will be c, self dot n iters will be n iters, right? Okay, let's define weight and biases as well here and provide initial value as a none. Okay, self dot b is equal to none, right? So this is all about constructor. Now this is fit method. So fit method will require xtrain and y-test, right? Okay, so first we need to initialize our weight, right? Self dot w will be, let's say initialize with zeros, it would be shape of xtrain dot shape of 1. So number of column in xtrain would be our number of features, right? And weight should be a same shape. Let's self dot b is equal to 0, right? Now we need to perform, we will perform a stochastic gradient descent here. So basically we will update our weight for each point, right? So let's first iterate over number of iteration, right? We have defined range self dot n iters. Okay, now we need to iterate over all data set, right? Let's say for we can consider like this: idx index and xi in enumerate x, right? Or let's say we can define a zip as well. Write in that way. Okay, let's say for xi yi in zip of x train and y train, right? So here, first of all, here we had what, y train. Okay, so here it would be y train, not y test, right? Okay, so now we had our constraint, right, that yi into w transpose xi should be greater or equal 1. So if it is greater or equal 1, then there is no loss, right? So we will not apply, I would say, loss while we are applying gradient descent, right? So we'll just use as a w term. So if I see here, if you let me go there. Okay, so if you see this term, for this term we had constraint, right? This will be only positive, or basically our loss, when we are misclassifying thing, right? Agree? So if it is not greater or equal, let yi into w transpose xi is not greater or equal 1 here, then there is a eta. If it is greater or equal 1, then we don't have any loss, right? So we don't have to update weight respect to loss. We will use this w there, but not this term, right? Okay, so let's go there. Okay, so let me define one condition. Condition would be yi into np dot which is self dot w and xi, right? So we are iterating over each data point, and we will update our weight accordingly, right? W transpose xi plus it would be self plus b, right? So W transpose xi plus b should be greater or equal 1, right? If it is, then we don't have any loss in our equation, right? So let's say if this condition is true, then we don't need to update a bias, because let's see here, we have only bias term in this part, right? Here we don't have any bias term. So while condition is true, yi into w transpose xi plus b is greater or equal 1, then we need to update just to weight with respect to w, right? So let's write that code here. If condition, my self.w will be self.w minus self.learning rate into self.w, right? Because the norm of w divided by 2, norm of w square divided by 2 will be w with when we are differentiating with respect to w. Here we had seen, right, this term, right? So we need to just update weights. Okay, so I can rewrite it as like, let's say, minus equal to, right? Okay, if this condition is not true, then we need to update our weights. So what would self dot w will be, let's say, minus equal to self dot learning rate into self dot c, right, into self dot w. Here it is a capital W, right? It's typo there. Self dot w minus np dot yi into xi, right? Xi and yi, right? Same for self dot b minus equal to yi self dot c into yi, right? And let's multiply it with learning rate. So I can write self dot learning rate into self dot c into self dot, or basically yi, right? here what I am saying is this term, right? So we had used w minus c times yi into xi. If you see here, yeah, w minus yi into xi, and for b we are using c into minus yi, right? So here self.learning rate self.yi into minus yi. Okay, so this is all about a gradient descent for the SVM classification, right? So let's implement a predict method. So predict method would be, let's say we need to just do w transpose xi, right? And we will use the sign of that to predict whether it is a -1 class or +1 class. So let's say result is equal to np self.w, and we would require x here, right? X. So let's say there are multiple x we are getting at a time, so we can write the for loop to simplify it. X in x, let's me write new predictions is equal to empty list, right? And we need to apply x plus b, right? So it would be self.b, right? So if I am getting a negative value here, then my class would be -1, right? And if I am getting positive value here, then my class would be +1. So let's I would say get the sign. So there is function like np.sign and pass the result, so it will return -1 or 1, and we will append it predictions dot append. Okay, and let's return predictions. So this will be our implementation for soft margin SVC, right? So let's use this. So first we need the data set. So we will, as usual, we will use sklearn library. From sklearn dot datasets import make classification. Okay, let's say import from sklearn model selection import trend test split. Let's import some metrics as well. Let's say from sklearn dot metrics import, let's say accuracy score and confusion metrics, right? Okay, so these are few functions which we would require. Let's find x and y is equal to make classification. Let's say n samples is equal to, we need 1000 samples, right? And let's say in features equal to 15 features. Okay, so we now get xy. Here if you see y, we will have 0 and 1 values, right? But for our SVM implementation we would require -1 and +1, right? So let's change y of y is equal to 0. So we are converting 0 with -1 here, right? Now our y will be in form of -1 or 1. Okay, so let's train our model. Let's say SVC is equal to soft margin SVC, right? We are just using default parameter here, learning rate C and number of iteration, right? Let me copy here. What happened? Okay, so svc dot fit. Okay, so first we need to divide our dataset into train test split, right? We forgot that. Let's say xtrain ytrain xtest and ytest is equal to and test split x y test size, let's say 0.2. That means 20% data would be considered as a test data set. Okay, so okay, I think it would be like this. Y train. Okay, let's fit X train, Y train. Okay, it will take time. Let's write the code for. Okay, what's the issue? Object has no attribute W. I think there is a typo. Yes, we need to use capital W, right? Let's see other places. Okay, it's look fine. Let's rerun. Okay, so let's get trend prediction is equal to svc dot predict x trend, same for test prediction test. Okay, so now let's see accuracy here, right? So print, let me use app string here. Train accuracy is accuracy score of x would be small, okay, y train and train prediction, right? Same for a testing set. Let's say test accuracy would be y test and test prediction, right? Okay, so let's run and check it out. Okay, so for training we receive 0.93 accuracy and test we receive 0.94. It is basically 93% in training and 94% in testing, right? So let's print confusion matrix as well. So let's say print train confusion matrix would be app string confusion matrix of same y train and train prediction. Okay, so let's do for testing as well. Okay, let me correct this. Okay, yeah, so y test and test prediction, right? Okay, so let's check it out. Okay, let me write it this way, it would be better. Okay, so here we see confusion matrix is also good, right? Not bad. So now let's see for the sklearn implementation part, right? So let's say we use SCD classifier with hinge loss, right? So we can use, like, let's say from sklearn dot linear model, because SVM is linear model, right? Import SGD, C would be capital, classifier. Okay, let's say CLF is equal to SGD classifier. Let's say same max iters is equal to 1000, right? And CLF dot fit our X train and Y train, right? Okay, So by default it used the hinge loss, which is basically SVM, right? So if you see here, the loss is default hinge loss, so we haven't specified that. Okay, so let's see the accuracy term. So let's first predict here. I am just reusing the same variable, right? And I will just change this CLF, okay. Okay, let's use this. And let's print confusion matrix as well. Okay, right. So if you see in sklearn implementation, we also receive 92% accuracy, right? Which is very similar to our implementation, right? The accuracy are almost similar in our implementation as well, and in SGT classification as well from the sklearn, right? So we can say we had implemented a good version of soft margin SVM, right? So this is all about SVM classification implementation from scratch. If you like this video, please press like button and subscribe my channel and share it with your friends so they also can learn, right? We will meet in the next video. Thank you.